the recording. Okay. So first, this is the frame problem, the one problem in the last homework. So let's work on that. Now, um, let's first, you can see this frame structure here that I just reproduced. And I split it up into the three members. So you have 3, 1, 2, 3, and the coordinates are numbered as 1, 2, 3, 4. So first step is we can write our fixed end moments first. So here my moment is 4 kips per, my distributed load is linearly varying. It's at 4 kips per foot at the bottom. So right now let's open the chart of fixed end moments. And you can see it is here. So you have WL square by 20 at this end and WL square by 30 at the other end. So let's write the loads first. Um, so if you calculate WL square by 20, let me take my calculator. So W is 4 and the length is 10 feet. So W times 10 square by 20. So that is 20. So therefore, sorry, this is the moment. So $20 kip foot on this side, and on this side, WL square by 30. So 13.33 kip foot. Okay. Okay. And what are the loads? So your load should be they should be balancing they should be satisfying force balance as well as moment balance. So we can find out first the load at this end. Okay, I will just do it here, or take moment balance about joint 1. Okay. Then what do you get? You have negative 13.33 and positive, whatever reaction is at that end, we will call it R2 times 10 feet, and then positive 20 equals 0. Uh, yes, this is okay. So this means R2 is 0.67667. So we are in step 1. This is fixed end moments. So I have oh, I have forgotten the load itself. Sorry. This is here, and then the load itself. So this will be negative 1/2 of 4 times 10 times 10 over 3. and this whole thing must be 0. So now let me calculate R2. R2 is 6 kips. And our total load is 1/2 of 4 times 10, that is 20. So on this side you have 14 kips. So these are the fixed end moments for element 1. Now element 2, we will do it in 2 parts. Like if you remember, for the last problem I sent the explanation. I'm not sure if you have seen it, but anyway, we will do it in 2 parts. So this 75 kips force, we will resolve it into 2 components. Uh, one component along, one component perpendicular. So let's see the dimensions of this triangle. So I have here 15 feet, I have here 12 feet. So this triangle is, let me make it here. Please let me know at any point if you cannot hear clearly. Okay, so this triangle here is 12, 5, 30. That's the Pythagorean triplet. So I have in the center a load acting like that, and also at the center a load acting like that. So what is the load perpendicular? That is 75 times 5 over 13, 28.846. Sorry, 75 times 12 over 13, 69.231. So that is this load, and along the member is 75 times 5 over 13, 28.846. Okay, so I need to have equal reactions on either side since it's at the center. So each of those reactions will be 14.423 kips. Now, for a load at the center, what are the fixed end moments? And what are the reactions? Fixed end moments are PL by 8, PL by 8, and reactions are given P by 2, P by 2. So 69.231 P times L. L is 13 feet. So PL by 8 comes to 112.5. 112.5 kip foot. 112.5 kip foot. And 69.231 by 2 is 34.616 kips. Now we will combine these two. This plus this is equal to what kind of fixed end moments you get. So as you know, your moments, they don't depend on, moments are only due to the load perpendicular to the member. So therefore you have uh, 112.5 kip foot, 112.5 kip foot, and these sorry, I don't know why the Zoom suddenly stopped. Maybe some internet issue. But if at any point you all did not hear, please let me know. I think I need to do the share screen. I think the recording did not stop, but something went wrong. Okay, anyway, please at any point of time, if you cannot hear, please tell me. So we split this inclined member into two parts, and the moment at the ends is 112.5 kip foot. Now, this reaction, this reaction, and this reaction, they both will get added up to produce purely vertical reaction that will be equal to 75 kips over 2. So you will have here 75 over 2, that is 37.5 kips. And here another 37.5 kips. Just a second. Hello, hello. Okay. Yes. Yes. Uh-huh. Who? Oh, yes, yes, yes. I will do that. Yes, parking. Oh, okay. Then one for Zilan, one for Dustin. Yeah, I will do it. Yeah, yeah, yeah. I will email you. It's now at 5, right? Yeah. Oh, it's at 3 to 5. Okay, I will email. Yeah, and get the parking. Okay, okay. Thank you. Okay, bye. Okay, sorry. So here are the reactions: 37.5, 37.5. And the moment. So we got fixed end moments and reactions for, you can confirm. So if you add up the components of this 34.616 times 12 over 13 plus 14.423 times 5 over 13. So we got exactly 37.5. Okay. Now the last member, it does not have any loads along the length, so no fixed end moments. Okay, so this here we finish the fixed end moments. Now let's mark the coordinates so that we can get the global stiffness matrix. So what are the coordinates? Let's mark origin at joint 1, 0, 0. Then this will be 0, 10. This will be, just let me write one thing. Okay. So 3. This is X is 12 feet and Y is 15 feet. Okay. Now here X is 12 plus 8, 20 feet. Y is 0. Okay. Now we got all the coordinates. Maybe I'm going to send this file after the recording is finished, but right now we are going to enter in MATLAB. So if you want to take a screenshot, you can take it. Okay, you took it. Now I'm going to MATLAB. Now the same frame file that I sent you all earlier, just make a copy of it and we will save it as frame problem 1. So there is only one problem. So first one is 0, 0. Second one is 0, 10. Third one is 12, 15. Fourth one is 20, 0. Okay. Just a second. Just a second. Okay. Now connectivity is same. Member 1 is between joint 1 and joint 2. Member 2 is between 2 and 3. Member 3 is between 3 and 4. So the global degrees of freedom, they still will not change. If you remember, you run to here, global degrees of freedom, 1, 2, 3, 4, 5, 6. 1, 2, 3 joint 1, 4, 5, 6 joint 2. Remember, for frame you have horizontal, vertical and rotation. Okay, so now let's calculate all the direction cosines, everything, and then we will come to the member properties. So the member properties for here, 29,000, area is 10.3. Let's revise that. 10.3 square inch for all of them. And moment of inertia is 285 inch to the power 4. Okay. Now till this point we are good. Let's come further down. So we should be arranging all of the local stiffness matrices. Let's arrange that, and global as well should be fine. So let's come all the way up to global assembly. Okay, before the partition, let's do everything. So where is K global? Looks to be fine. All right, because the code is working fine. Okay, I made sure before sending to you all. So here is we got the global stiffness matrix. Now let's go back. So next is we have to make the vector of fixed end moments. So if you remember this equation, K U plus the fixed end moments, this is what is equal to the total applied forces. So this is true for each member, also for the total frame as a whole. Okay, so let's see what is our stiffness matrix. It will also be, you have 3, so 12 by 12. So let me just paste the same figure, pick it up from, so that we don't need to draw again. Pick it up from here. Actually, I'll just pick up. I don't know if you all got a chance to see this slide, but no problem if you did. So we will assemble the stiffness matrix. Yeah. So we don't have this. We'll see this later. Okay. So this is what we have in this problem as well. Now let's arrange the fixed end moments vector. Okay, so sorry, here we have one more thing. This is this plus the vector of fixed end moments. Okay, so I'm going to make a picture here. Maybe you can take a screenshot as well, so that we can go enter the fixed end moments into.
Dr. Nathan.
Yes.
How did you get 37.5?
This is 75 kips, right, Kehinde? So half of it will go to either side.
75 kips.
Here is 75 kips, right?
Okay, okay. Then what about the 150 here? The 150 kips there.
Yeah, that's at the joint, so that will not come, that will come under when we enter the external load. It will come on the right side of the equation.
Okay.
So let's enter those now. Yeah, I took the screenshot. Okay, so what are the fixed end moments? So for the first one, I hope you took this screenshot here. So I'm entering those fixed end moments now. Let me just make a few lines that will make it easier. Give me 1 second. Okay, so that's, let's put nice ones here. Now let's write the fixed end moment. So what's the 20 in at the very bottom? We have 20 going counterclockwise. No, first is we need to write the horizontal force. So you have 14 keeps going to the left, so minus 14. Then you have, you don't have any vertical force, so 0. Then you have 20 counterclockwise, so that is keep foot. Let's convert to keep inch, so 240. Counterclockwise, so positive, so positive 240, right? Then second joint, okay, second joint you have 13.33 going clockwise for this vertical member, and for the inclined member you have 112.5 going counterclockwise. So totally you have 112.5 minus 13.33. So that is 99.17. That is keep foot. So in keep inch, you have 1190.04. Okay, let's put that. Oh, that's the moment for this one. So 1, 2, 3. It will go here. 1190.04. Okay. Then what is the force here? Horizontal force. You have 6 kips going to the left, so you have -6 here. Then no vertical forces, so 0. So that is fine. Oh, you do have vertical force from the second one. That is 37.5 going up. So that is adjusted fine. Now let's come to the joint 4 or node 4. You have 112.5 going. Okay, first you have horizontal force. Horizontal force is nothing, so put 0. Vertical force you have 37.5, so put 37.5. And moment you have 112.5 going clockwise, so negative, multiply by 12, so 1350. So you have 1350 negative. And okay, now last joint you don't have anything. Okay, now among D1, D2, D3 and all of that, what do we know? So the joint 1 and joint 4 both are fixed supports. So D1, D2, D3 goes to 0. D10, D11, D12 goes to 0. And then we know, let's see, P1, P2, P3, we don't know. P4, P5, P6 all are 0. P4, P5, P6, because at joint 2 we don't have any loads applied. Then P7 is -150. Then P8 is nothing. P9 is 0. Okay. Then P10, P11, P12 we don't know. Okay. Just a second. Okay, we have all of these. Now, what is our partition? How should we partition our matrix? So the known degrees of or the known loads are all of these from 4 to 9. Okay, from 4 to 9. So actually the partition what I showed you in the previous one. It is same 4 to 9. Okay, the rest are 0, right? So you just partition from 4 to 9. Then you have your fixed end moments. So, and all the fixed end forces. So let's enter all of these now. So you can make a screenshot of this. It will take a second to make a screenshot. Okay, if you have done that, I'm going to enter all of these fixed end moments. Okay. So F is, I have negative 14, 0, 240, negative 6, 37.5, 1190.04, 0, 37.5, negative 1350, 0, 0, 0. Okay. There we go. And then this is F partition is same. P partition is these loads. Okay. P partition is all these loads, the one we already know. Okay. So only P7 is negative 150. So we have all zeros. 1, 2, 3, 4, 5, 6. Same number. So P4, P5, P6, P7. Here is negative 150. Okay. So now it is fine. So let's run the whole thing. So now let's check the forces. So now what we need to check is whether our equilibrium is satisfied first. Okay. So let's just a second. Okay. So all of you took a screenshot of here. Oops. Of this one. Just take a screenshot. Now let's go check all our total vertical load. So first we can check sigma y. Okay, sigma y. So you have only this one. This is the second one, right? It is x, y, and moment. So second one, this one, and the last one, 75 kips. Okay, 75 applied down, 75 up is balancing. That's fine. Now let's check horizontal. Let's check horizontal. So you have totally, what's the horizontal force? So you have 150 to the left, and you have this thing is 1/2 of 4 times 10. So 20 to the right. So totally you have 130 to the left. So you must be getting positive 130 total. So this plus this. Okay, so that is balance. Then moment. So moment balance, let's take balance of all moments about 1. Okay, so I'm going to copy these moments here from the MATLAB. Uh, so what are the moments? Let's see. So you have negative 5875 here. Okay. Let's first write the forces. Horizontal is 78.787 here. Vertical is 128.118 here. Then negative, so clockwise. So 5875. Let me convert it to kip feet. Back to kip feet. 489.586. Okay. Now here, what is your reaction? $51.2 to the right. Vertical is downward. $53.118 kips. Moment is again clockwise. Convert to kip feet. $181.379. Okay. Okay, now let's check moment balance. So we will write here sigma fx is 0 is satisfied. Sigma fy is 0 is satisfied. And sigma m at, let's check joint 1. So you have negative 489.586. Then you have, what do you have due to this 4 kip feet? So you have negative 1/2 of 4 times 10 times 10 by 3. Then you have negative 75 times 6. Then you have positive 150 times 15. Then you have this moment, negative 181.379. Then you have this one, negative 53.118 times 20. So let's check, is it all okay? Seems fine. So let's write all of them. So that is negative 489.586. And then this one is 20 times 10 by 3, 66.67. So negative 66.67, then negative 450, positive 2250 negative 181.379 negative 1062. Let's add up all that. Okay, so we will get 0.005, which is so we are okay, satisfied. Now that is clear. That's how you do this thing. I hope that is clear.
Dr. Nathan,
Yes.
in your code for 190, you didn't put minus. Should it be minus or positive?
Let me see.
In the F, for the F.
Yes, let me see. Let me see. Positive.
Positive?
Yeah, 1190.0.
Yeah. Okay, thank you.
Look, which joint is this? 1, 2, 3, 4, 5, 6. So second joint, the moment at the second joint, right? It is, see, this is 13.33 clockwise, but at this, for the member 2 at this joint, you have counterclockwise 112.5, right?
Right.
So counterclockwise 112.5, that is positive 112.5, negative 13.33. How much is it? 112.5 minus 13.33. 99.17. You convert to kip inch, 1190.04, right?
Yeah. Thank you.
Okay. So, I mean, I know that we have to send, while we solve, we have to send this vector of, so this is the fixed end moments. This is the K. This is the D. And this is the external forces. So we have to send this to the other side. So that's why in the code you have minus here, right?
Yes.
Okay. So this is okay. So let's move ahead. Now, see that's why I was saying you were I think many of you were panicking very quickly. So you don't worry. So if you have the code, it will not take that long. Okay. So of course, if you do from scratch, if you're writing then I agree. It is way too much. But don't what I'm saying, don't get worried, because it's once you have the code, and I already checked the code is working, so it should be okay. Okay, now let's go to the final. Okay, so yeah, and now I know why the truss problem, it looks very big, but don't worry, we are going to do it now. Let's open the truss code first. Or let's do one thing, we do the final backwards. Since we have the frame code already, we will go use that. So now let's save it as So what do we do now? Here is your frame, and let me put the picture in the.
Dr. Nathan, I have an issue.
Uh-huh.
When I run the code,
Uh-huh.
I get different forces.
You get different forces. Okay. Let's do one thing. Can you share your screen?
Yeah.
That does not look okay. So can you go to your code? Oh, Samal. So that's why, because you entered the moments in keep foot instead of keep inch. So on your line 64, how come you have only 64 lines?
You mean here?
Just a second. No, I'm just saying what. Oh, you removed the needless comments. That's why. Okay. Yes, there. So that is 14, 240, negative 6, 37.5, 1190.040, 37.5. Oh, seems fine. Wait, just a second. Oh, okay. I think you might have not. Can you open the rotmat file? See, it's to the left in your current folder. Can you just double click the rotmat? So there was an error there, and yesterday that's why I sent the updated one. But yeah, you can open the rotmat. It's taking a while to open. There you go. So yeah, that's the can you fix that? So see, there is cosine t. Next should be sine t, not negative sine t. Wait, wait. Let me take your permission. Can you accept the? Okay. So can you run now? Can you run it, Samal? Can now type or go to the command, go to the variables. Oh, yeah, whatever. Type format long G. Space long space G. Enter. Now again type forces. Still something is not matching. Okay. Can you show your K global? Let's compare the K global. This one seems fine. Okay, go back to your frame homework. Fine. Can you scroll up a little bit? Some more. Wait. Okay. Can you come down? Some more. All the way. Just a second. Okay, let's do one thing. I think if we are debugging this, it's going to take a bit of time. So what we will do is I will send you my folder, or I will send all of you this folder, and then you run this one. Okay, there somewhere some small thing is different. That's why. But instead of because right now at this moment we don't have enough time to debug, but we will a little later. But for now, I'm sending you just a second. So I just now sent to all of you. Okay, now let's come back. We are going to do this problem now.
Okay, you want me to unshare the screen?
Oh, yes.
Okay. Thank you, Dr. Ahmed.
Thank you. I hope you can all again see my screen now. So this is the frame problem in your exam. So again, the same steps. So first one, I mean, you can do either way. You can do first the global stiffness matrix, and then you can come back to do the fixed end moments, or any way is fine. So here I'm doing fixed end moments first. So okay. Again, one thing I hope you keep in mind, you know, how to explain. See, this is some very see the learning process is lifelong, right? You are learning every time. So the goal is every day we should learn something beyond what we know, what we knew yesterday, right? And it should be solidified. So what we learn, it should be solidified. That is, after this, if you want to apply, no matter where your job, or maybe you're just building something for your family with your hand, no matter what it is, if you want to apply, it should immediately come back, right? See, that's the main thing. I think um, even after like maybe you took, now it is 2022, even 20 years later, when you're fast asleep, still if I ask you, hey, what is this? Oh, you remember everything. It should be like that, okay? You should focus on that. I know exam is important and grade is important, but don't lose focus on the main goal, okay? That's what I'm saying. And if I think I heard on Einstein biography in his undergraduate, I think he was last, very last in his class, but maybe just one above the last, okay, lowest score. But he did. So now today, will anyone ask, oh, what was your score and did you get a 90 or right? It's completely irrelevant now, right? So that's why I'm saying, just don't forget the main thing, okay? Okay. I know this is important because when you go for a job, oh, they are going to check what did you get. So we are taking care of that here, but you need to take care of the long-term learning, okay? That's what I'm saying. Cool. Okay. So for this one, the first member has no loads acting on it, so no fixed end moments, right? Second one, you have 15 kilonewton per meter. So this you can break up as two parts. Oh, I'm sorry. This is the no, this is 15. Okay, this is anyway applied like this, so we don't need to break it up. So we have, what are your end reactions and your fixed end moments. So this is WL square by, if you remember, 12. Those are the fixed end moments. You remember from your WL square by 12, right? I think one more thing. See, it's like this, okay? It's like this. Now you're all becoming engineers, right? So in a very simple way, I'll only take 1 second to tell you, very simple way. So let's say you have workshop. Maybe there is Armin here. He will know better than me. Now maybe let's say you need to build some structure or some complicated maybe framework or something. Let's say that all that you have in your hand is maybe uh, uh, metal rod, okay, and you don't have any tools, nothing. Yes, still you can somehow build, but it's going to be very, very difficult, right? But let's say now you have everything in your hand. You have what not, you have maybe lathe, then you have all kinds of the cutting machines, then you have your files, and you have your power tools, and you have now you can build in no time, right? So that's what all this is, this matrix method, this mechanics, this mathematics, physics, this is all like this, okay? These are like tools in your engineering. So you should make them as a tool, okay? Okay, so what is the WL square by 12? So this is 15 times L is, so this is 13. So length of that inclined member is 13 meters. So WL square by 12, 211.25. So you got 211.25 kilonewton meter at each end, right? Okay. Now, what are these two forces? You have 15 kilonewton per meter on 13 feet. So you have 195 kilonewton, and this over 297.5. 97.5. Okay, so this you need to break it up into two components. So you have your 97.5. Just a second. Okay, you have 97.5 kilonewton acting that way. So we can break it up into horizontal component and vertical component. Okay. So how much is it? 97.5 times 12 by 13. So that is 90. So you have 90 kilonewton here, and horizontal is 97.5 times 5 by 13, 37.5. So this is what you have at each end, right? Okay, so now if you took a screenshot of this, let's put the coordinates as well here. So you have 0, 0. Here you have 0, 10. Here you have 12 and 15. That's what you have. Now, if you took your screenshot, I'm going to enter this in MATLAB. So this is 0, 0, 0, 10, and 12, 15. Oh, it happens to be the same. Okay. There is no last one. Okay. Then connectivity, you have 1, 2, and 2, 3. That's all. And global degrees of freedom, how many you will have? Number of members, and for each member 6. Yes. So then I think this should be direction cosines and lengths. Okay, this is fine too. Then you have your member properties. You have only 2, so you can remove the third one. And what is your E? 70 gigapascal. So we will enter everything in kilonewton and meter. Let's see. Kilonewton and millimeter, that may be best. Okay, so let's convert here. Convert the properties. So E is 70 GPa. So this is already 70 kilonewton per millimeter square. That's fine. A is okay. So it's already in the correct unit. So this is fine. So let's put the same. E is 70. A is 4570 and I is 34.5 times 10 power 6. And 70 again. A is 4570 and I is 6. Okay. So okay, this is fine. This is okay too. And I think should be okay as before, all the way up to the partition. So let's look at K global, and it should be 9 by 9. So that seems to be fine. Let's go ahead now. Oh, the length. We need to fix the length. The length is right now, we got it from the coordinates were in meters. So the length we need in millimeters. So we need to multiply by 1000. So let's run again up to partition. Should be okay. 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 So so now we go and we make the matrix. Now our stiffness matrix is going to be 9 by 9, right? So just a second. Okay, here is our stiffness matrix, and this times your K times U, plus you will have your fixed end moments. And this should be equal to okay. There. Now, what are your fixed end moments? So you have nothing for this end. 0, 0, 0. Then what do you have at this end? You have horizontal is negative 37.5. Then vertical is positive 90. Then moment is 211.25 kilonewton meter, but we want it in kilonewton millimeter. So 211250. Counterclockwise is positive. So 211250. Then come to the last one. You have again 37.5 negative. Then you have 90 positive. Then you have clockwise, this one. Okay, so then here you have D1, D2, D3, D4, D5, D6, D7, D8, and D9, right? Then, yes.
Negative for the last one. Negative 211. 250.
I forgot the negative. Very good. It is clockwise. Yes, you are correct. Thank you. That's what, right?
Yes.
Thank you. Thank you. Very good. So now you have P1, P2, etc. The external forces. P1, P2, P3, P4, P5, P6, P7, P8, P9. Okay. Okay. So now which ones are let's check D1, D2, D3, and D7, D8, D9 are all zeros, right? So let's mark that. So D1, D2, D3 are all zeros. D7, D8, D9 are all zeros. We have fixed support. Then P1, P2, P3, P7, P8, P9, we don't know. And P4 is positive 160. And P5, P6, we don't have. So okay. Okay. So now we can go ahead to solve it. So our partition should be only 4, 5, 6, right? So if you want, you can take a screenshot. Now I'll go enter in MATLAB. Okay, we entered already all this. Yes. Okay. Only 4, 5, 6. And now F. fixed end moments, 0, 0, 0, negative 37.5, 90, 211250, negative 37.5, 90, negative 211250. Now that is F partition here, and our P partition is 160, 0, 0. And total displacement, this is only 9. Here we have okay, we will automate this also. Okay. Here we have total is only 456, and now this should be fine. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So let's run it. Let's check our forces. Okay. So let's check whether our equilibrium is satisfied. So I'm going to enter the MATLAB reactions here. So I'm sorry, the internet was kind of out. I think you could not hear anything for some time, right?
I can hear, but it's just saying sometimes I lost your video, but I can hear your voice.
Okay. Thank you. So yeah, the internet almost dropped and the Zoom reconnected. But anyway, we are going to enter the support reactions now. This is 17.636 kilonewton. So this is 167.971 kilonewton. And this moment is clockwise, 5858.196 kilonewton meter. And at this end, you have horizontal negative 252.636 kilonewton, and upward is 12.029 kilonewton. Moment is clockwise again.
I don't think we could see screen.
Oh, it lost the share screen. Thank you. I think it was Kyla said, right? Okay, thank you, Kyla. So, I was writing all these reactions here, all the reactions, just copying from MATLAB. And what is the 258.201? Kilonewton meter. Okay. Okay. So we have all of them now. Now let's check the equilibrium. So how about sigma fx? So let's see, you have you have 17.636 positive, then you have 160 positive, then you have, okay, let's see, this is 15. So what is the horizontal component? 15 times 15 times 5 over 13. So 5.769 something. And this is length of 13. So 75 to the right. And then 252.636 to the left. So what's all this? 17.636 plus 160 plus 75 minus 252.636. Okay, 0. Then check sigma Fy. Okay, you have 167.971 upward. Then, so how about the 15, that one? 15, the component downward is times 12 over 13. So 13.84, these many kilonewton per meter over 13 feet. So the total vertical load is 180 kilonewton. So negative 180. And then positive 12.029. So that is 0. Then let's take sigma m about joint 1. So you have 58.196 negative. Then you have negative 160 times 10. Then you have you can take both of these separately. So the 15, you have 75 kilonewton so horizontally. So negative 75 times. So for the 75, your lever arm will be 12.5, halfway from the bottom. I mean, halfway from here. And then the vertical is 180. So you will have negative 180 times, so 6. Okay. Then you have negative 258.201. Then you have positive 12.029 times 12. Then you have positive 252.636 times 15. Let's call that negative 58. Okay, let's just do it on the calculator. Negative 58.196, negative 160 times 10, negative 75 times 12.5, negative 180 times 6, negative 258.201 positive 12.029 times 12, positive 252.636 times 50, 0. Okay. So equilibrium is satisfied, and that should be fine. Okay, let's go to the next one. As Kyla mentioned, the truss, maybe you have some issues, so let's do that one. Yeah. Now, let's open the truss code. Let's just open one of them. They are all the same code. Oh, we didn't we write much? Let's see. Here we go. Okay. So truss final. So now let's mark out all the joint coordinates. So you have a lot of connections here. Okay. So let's start 1 at origin, 0, 0. So 2 is going to be, maybe we can write here, 1, 0, 0, 2, 5, 0, 3, 10, 0, 4. Where is 4? Here. 4 is 10, 16, 22, 0, 5, 27, 0, 6 is 32, 0. 7 is, and this is 8. So 1, 2, 3, 4. So 2. So 7 is, let's see. Let's look at this small triangle for 7. This is 5. This is 2. Okay. And this is, this is 8 at 4 meters. So let's see how many supports we have. 1, 2, 3, 4, 5, 6, 7, 8. Okay. 2, 3, 4, 5, 6, 7, 8. Okay, so this is 4. So this is 4. So for 7, number 7 is going to be 4, 2. 4, 2. Number 8 is going to be so 8, and the height is 4. Number 9 is going to be 12, and the height is 6. Number 10, height is 8 and 16. Number 11, 1, 2, 3, 4, 5, 20, and the height is 6. Number 12, 24, and the height is 8. I'm sorry, height is 4. Number 13, 28, and the height is 2. And number 6 we already did. Okay. Now number 14. Number 14 is here. Okay. Let's see. Number 14, height is same as number 12, so 4. And distance, number 14 is midway between these two. Let's see, is it midway or not midway? Not midway, okay. Not sure. Let's just calculate for 14. So you have this is joint 8, 9, and 14. So 8 is 8, 4. Okay. 9 is 12, 6. It's 2. This is 4. So let's calculate this length, 8 to 9. And then we can get this one. Okay. Oh. Okay, you can all hear now, is it? I again lost my Zoom. Can you all hear now? I'm going to switch to.
Yes.
Okay, thank you. I'm going to switch to the Ethernet. Just a second.